This is Module 8, Protein Metabolism. In this video, 8-2, I'm going to talk about the different pathways involved in oxidizing amino acids so that you can generate ATP through their catabolism. Amino acids can be oxidized in many different ways, but they're typically converted into intermediates of the citric acid cycle, intermediates of glycolysis, or actual substrates of the citric acid cycle. And so this image was shown to you in the first video, 8-1. And I really just focused on talking about this, how proteins are degraded and then used to either build enzymes, cell walls, what have you, muscle tissue, and things like that. Now I'm going to go one level down where we take those amino acids and use them to generate ATP. And so amino acids can be converted into glycolysis intermediates, as you see here, or they can be converted directly into pyruvate, which can be converted into acetyl-CoA and funneled into the citric acid cycle. But many amino acids can also be broken down and used to replenish different citric acid cycle intermediates, such as fumarate, succinyl-CoA, alpha-ketoglutarate, and oxaloacetate. Some can also be degraded directly into acetyl-CoA or precursor to acetyl-CoA. So what is the process of breaking down an amino acid when you're going to use it for energy production? And so if you don't use the amino acids to build proteins or other types of body tissues, you can catabolize them and use them for energy. It's not as effective as using glucose or lipids. And so you really only break down amino acids during times of metabolic need. When you have too many amino acids, remember, you can't store amino acids, so you either use them or you lose them. So you can use them to build other things, or you can break them down and use them to create ATP. So what happens when you do that? I'm sorry. So what I was going to say was you only do that if the body is starving and you don't have access to other more higher energy molecules like glucose and lipids. Those ones can be used to generate more ATP, whereas using the carbon skeleton to generate ATP from an amino acid doesn't make as much ATP as lipids or glucose. So you're really only going to use amino acids for this process if you have lots of them to spare and you've got to get rid of them, or you're starving and you don't have access to glucose or lipids. Okay, so the first stage of an amino acid catabolism is removal of that amine group. This is fairly toxic and it can't be used for any part of central metabolism. And so you have to remove it and get rid of it. That leaves just the carbon skeleton behind. So this would have to be removed from any R group. And then once this is removed, and there are some that also remove the sulfur R groups for amino acids that have sulfur R groups. But the remaining molecule is composed of a carbon skeleton, which has various levels of reduction already involved. So different amino acids that, an amino acid that's already been, that is more reduced will generate more energy. An amino acid that is less reduced will generate less energy. That carbon skeleton can either be completely oxidized into central metabolic pathways into carbon dioxide and water. So this would be your best situation where it can enter right into central metabolism. Say it's turned into pyruvate. It can be used to build glucose. It can be converted into glucose and then funneled through central metabolic pathways. It can be converted into acetyl-CoA, which means it can only enter in at the citric acid cycle level. So you skip over glycolysis and do only the citric acid cycle. And so you can imagine an amino acid that generates a carbon skeleton that can only be converted into acetyl-CoA will not result in as much ATP production as one that can be converted into glucose, since by converting it into acetyl-CoA, you skip over the entire first stage of central metabolism. And so you have fewer reduced electron carriers as a result. They can also be oxidized or converted into ketone bodies, which can be converted into acetyl-CoA and then used in the citric acid cycle or used directly by the brain as a source of energy during times of extreme starvation. So again, these will not generate as much ATP as these would. And so I'm going to go through stage 1, what happens to this extra ammonia, because this is very, very toxic if concentration becomes too high. It's also really toxic to body tissue. And so you can't simply dump ammonia into the bloodstream and let it travel to your kidneys. It's too toxic for that to occur. It would cause all kinds of damage on its way to the kidneys. So I'm going to talk about this, and then I'll talk very briefly about some of this stuff over here too. To be clear, amino acid catabolism only happens in the liver. And so this is only happening in the liver. We can only break down amino acids to in the liver. And so the carbon skeleton can be released into the bloodstream and then other tissues can do it, but only the liver is able to remove that very toxic amine group. And so the very first stage of amino acid catabolism happens in the liver. Okay. So the first step in the catabolism of most amino acids is a process called transamination. So amino acids are funneled into or are repackaged as L-glutamate during the process of transamination. Okay, so here we have an amino acid, an L-amino acid. So this is any amino acid. So amino acids come in this direction. And then we transfer this amine group through this action of this enzyme, aminotransferase, to a molecule of alpha-ketoglutarate. And so the substrate for this aminotransferase is any amino acid plus a molecule of alpha-ketoglutarate. And then what comes out is L-glutamate and alpha-keto acid. And so we are consuming a molecule of alpha-ketoglutarate, which, if you recall, is coming from the citric acid cycle. And so we have to use a citric acid cycle intermediate here in order to get this amine group off of our amino acid. And then we generate L-glutamate, and then this remaining carbon skeleton. This will also happen for the R group of this amino acid as well, if the R group has an amine group attached to it. Okay, so now we've generated a glutamate molecule. And so that glutamate molecule will bind to an enzyme called glutamate dehydrogenase to recreate that alpha-ketoglutarate that we borrowed for the first reaction. And so right away we can recycle the alpha-ketoglutarate that we consumed during this transamination step. And that will go back to the citric acid cycle. And so we net no real loss of alpha-ketoglutarate from this process because we recreate it right away. So it's just, so now we have, and during this process, we also reduce an electron carrier, NAD to NADH. So this glutamate dehydrogenase process will actually contribute to ATP production in the electron transport chain. And so once this occurs, we now have a free ammonia molecule or amino group. And so now we have to repackage that so that it becomes less toxic. The resulting alpha-ketoglutarate, like I said, heads back to the citric acid cycle, netting no loss or increase in this intermediate through transamination and this process. And then we also contribute to ATP production through reduction of electron carrier. So what happens in the urea cycle? Let's take a look at that. Ammonia is really toxic. You can't simply dump it into the liver cannot just excrete ammonia in this form without causing major damage to tissues in the body. It's very toxic. And so it has to be converted into something that's less toxic in order to get from the liver to the kidneys where it can be expelled as waste. For us, for mammals, we do this by converting ammonia into urea. This is not done in, say, fish and aquatic animals because they're small enough that they can excrete it directly into the aqueous environment. And so they have a situation where their bodies are constantly diluted with water. And so that makes ammonia less toxic for them to transport. But we don't have that benefit. And so we have to transport it as something less toxic. Urea is still toxic, so we still need to get it out of the body before it can start to cause damage. But at least ammonia or nitrogen can travel through the body safely in the form of urea without causing damage. This happens in the liver. So before exporting ammonia, the liver will turn it into urea. 2 nitrogen groups have to enter the urea cycle in order to create 1 molecule of urea. one of those nitrogen groups enters as a molecule of carbomoyl phosphate, and I'll explain why in a moment, and the other enters as a molecule of aspartate. I'll explain that as well. Urea then makes its way into the bloodstream, so it's exported from the liver into the bloodstream, transported to the kidneys, where the kidneys will excrete it as waste. And so we are able to safely remove the amino group and expel it. So let's talk about that first step here, where nitrogen will enter the urea cycle as a molecule of carbomoyl phosphate. Here is an entire summary of the urea cycle. So here's that transamination step that I was talking about, where any amino acid comes in, the amino group is transferred to alpha-ketoglutarate, generating glutamate, and then we immediately remove that amino group using this enzyme, glutamate dehydrogenase, which recycles the alpha-ketoglutarate and generates a molecule of free ammonia. That will combine with a molecule of bicarbonate via an enzyme called carbomoyl phosphate synthetase, which creates this molecule of carbomoyl phosphate. That will enter the urea cycle and eventually be turned into urea. But in order to do that, we need a second molecule of ammonia, or another amino group. And so we can enter in another way through another action over here. So first I'll talk about this reaction up here with carbomoyl phosphate synthetase, and then I'll talk about this reaction over here through the action of a transaminase. So first let's talk about what carbomoyl phosphate synthetase is doing. Again, so during this first part of the urea cycle, we generate a molecule of ammonia. We then combine that with a molecule of bicarbonate, and then those are two substrates for this enzyme, carbomoyl phosphate synthetase, which is an ATP-dependent enzyme. We are creating a bond here, and so synthetase enzymes often require a molecule of ATP to do that. Not always, but often. Okay. This generates a molecule of carbomoyl phosphate, and this can enter the urea cycle. The second way in which nitrogen will enter the urea cycle is through that second reaction where we're creating aspartate. So here we have a molecule of glutamate that we created through a transamination step. That glutamate can react with glutamate dehydrogenase to generate ammonia. However, there's another fate that can happen where it reacts with a molecule of OAA, oxaloacetate, through the action of aspartate aminotransferase. And so it can, and so glutamate can enter the urea, or can be processed in one of two ways to get rid of that amino group. We're going to consume a citric acid cycle intermediate to do that, which is OAA. So remember, that's one of the two of the first starting materials for the citric acid cycle. So glutamate combines with oxaloacetate. I mean, not really. We're just removing this amino group and attaching it to oxaloacetate. That will regenerate alpha-ketoglutarate, just like the other reaction does, just like this reaction does, regenerates alpha-ketoglutarate. It also generates a molecule of aspartate by adding an amino group to oxaloacetate. All right, so this is the entire urea cycle in one place. So I'm going to point out some of those key reactions for you so you can see, so you can sort of orient yourself to this pathway. Okay, so first I mentioned how amino acids can be, you can remove that amino group and attach it to alpha-ketoglutarate to make glutamate. That glutamate will then enter the mitochondria, and that glutamate can be used by glutamate dehydrogenase over here, or it can be used by this reaction over here, which generates aspartate, which you're seeing right here, actually. Okay, so sorry, I skipped, I went to 2B before I showed you what was going on. Okay, so glutamate here enters the mitochondria. We can either remove the amino group and go the carbomoyl phosphate direction, or we can transfer it to a molecule of OAA, generating aspartate, and then it can enter in the urea cycle this way. And so carbomoyl phosphate is entering at step 1, aspartate is entering at step 2. Different parts of the urea cycle actually happen in different parts of the cell. And so the creation of glutamate happens in the cytosol, but the transfer of the amine group, so the release of the free ammonia molecule or the creation of aspartate, actually happen in the mitochondria. If aspartate is created, that's exported and back into the cytosol where it joins up with urea cycle enzymes here. The only step that's part of the urea cycle is step 1 that happens in the mitochondria. So this is the only step that of the urea cycle that occurs within the mitochondria. This, by the way, is the committed step of the urea cycle, the carbomoyl phosphate step. Okay. And so once a nitrogen enters this way, so we have this is our nitrogen molecule here. And then this is an ATP dependent pathway. The urea cycle is an ATP dependent pathway. And so it consumes energy in order to repackage 2 molecules of ammonia as urea. And so ammonia enters here at step 2B, and it also enters here at step 1, the committed step. And then we do more processing here to create urea. And so the steps that I'm asking you to understand are the steps of the urea cycle that creates ammonia molecules or amine groups to enter. And so all of these steps right here, and then obviously this step, which is related to this one over here. So you don't need to know any of these other intermediate steps. Let's talk a little bit about how this is regulated. The urea cycle is regulated by allosteric activation of carbomoyl phosphate synthetase. So when there's an increase in amino acid catabolism, there's an increase in the concentration of glutamate because of this transamination step that happens here. So this transamination step will increase the amount of glutamate in the cell. Increasing glutamate will result in increased amounts of this N-acetylglutamate, which activates the urea cycle, the first step, so the committed step. So this enzyme, carbomoyl phosphate synthetase, which is happening here, is the committed step of the citric acid cycle, and it's very tightly regulated, as you would expect, based on what we've learned from other metabolic pathways. And it's regulated by this molecule, N-acetylglutamate. And so when this occurs, when this amount increases, it increases to a concentration so great that it will very likely bump into this enzyme and increase the catalytic activity of this enzyme. And so it binds to a site other than the active site, which improves binding of this molecule to ammonia and bicarbonate to create carbomoyl phosphate. That's it. I'm not going to go into any other regulatory pathways, just that one. Okay, and so now we've removed the ammonia, and so what we have left over is a carbon skeleton with varying levels of reduction already involved, depending on the amino acid. So depending on the nature of the R group, basically. And so some amino acids, like I said, can be are more reduced and so can be oxidized fully. Others are less reduced and can only enter at the second stage of central metabolism, generating less ATP. Now, you don't normally break down amino acids for a metabolic energy. Unless you're consuming a good amount of protein or you're starving, you're really not going to do it that much. But in either of those situations, breakdown of amino acids accounts for 10 to 15% of your metabolic energy. So really not that much. The majority of your metabolic energy comes from oxidizing glucose or fatty acids. And I just want to make this final point here that some amino acids are glucogenic and some are ketogenic. And so I've sort of been alluding to this when I'm talking about this image here. Some can be oxidized fully through central metabolism. Others enter in at different stages and don't generate as much ATP. And so glucogenic amino acids can be degraded into pyruvate, which can enter the transition phase, be turned into acetyl-CoA. And so those glucogenic ones are these ones here. You do not have to memorize which specific ones are glutagenic and which are ketogenic. Just you need to know the difference between what these two terms mean. And so glucogenic amino acids can be degraded directly into pyruvate or into different intermediates that can be used to build glucose. And so they're called glucogenic because pyruvate can be used to make glucose in the liver through gluconeogenesis. And then these other citric acid cycle intermediates, alpha ketoglutarate, succinyl-CoA, fumarate, and OAA, can all be used as materials for building glucose. And so they would replenish the citric acid cycle, but they could also be used to build glucose in times of metabolic need by the liver. Ketogenic amino acids, however, can only be degraded to acetyl-CoA, and those are these ones over here. And those enter in the citric acid cycle, but they enter into a point where they can't be directly turned into glucose. So they could give rise to the production of ketone bodies. Acetyl-CoA can also be used to build fatty acids, but they cannot be used. These ones cannot be used to build glucose molecules.